Ladies and gentlemen, I'm Jing Liang from School of Automation's Chongqing University of China. Our paper title is Estimations of Leak Time Parameters based on fusions of leak behavior and data distribution characteristics from gas file sensor data. Today's estimations methods leverage only coarse time estimations and relies on expert experiments. So for granting automatic estimation of leak time parameters in a fine-grained time range. This paper presents a leak time parameter estimation framework fusing leak behavior and data distribution characteristics from gas file sensor data. It is important to find the leak parameters to conduct spill diffusion modeling and risk assessment based on the sensor data. This requires accurate estimations for not only the leak locations and the leak conditions, but also the time when the leak occurs. However, in most instances, the operators only knows the discovery time of leakage, but lack of awareness of the occurrence time, and the estimations of the occurrence time is in the coarse-grained time range and relies on expert experiments. This becomes a key and thoroughly inverse purpose for gas pipeline leak. The adaptability of liquid pipelines based on existing estimations framework is effective, but the ones on gas pipelines has not been proven, and the existing framework relies on a large amount of leak samples for training, but on the real-life scenarios, there are sparse leak samples. So we present a leak time parameter estimation framework. Under the proposed work, we use leak behavior characteristic extraction models for reducing disturbance of normal operating conditions and improve the estimation accuracies. And we use data distributions characteristic extraction models for realizing the automatic estimation and labeling of leak starting time for the perspectives of unsupervised learning. In order to verify the effectiveness of the proposed method, 2-liter gas pipelines in service in southwest China are used for field experiments. The data is from the vortex per section flow meters installed at the end of the pipeline. The leak samples include 69 leak events. The estimations result shows that the proposed methods had a higher degree of accuracy on all kinds of side leak, especially on medium side leak and large side leak. Slightly lower accuracies of small side leak may due to the behavior confusion between small leak and normal disturbance. The decision threshold sigma is an important parameter for inflection point detectors. We expect that the influence of sigmas on the estimation results is as low as possible. Therefore, we compare the accuracies of different decision thresholds. The results show sigma is an insensitive parameter, which indicates that the proposed method implement from the perspective of the data itself rather than relying on experiments. The confusions between small side leak and normal data fluctuations reduce the estimation accuracies of the proposed methods for small side leak. In future work, we plan to use deep learning methods to extract deep features from small side leak samples and find the abnormal boundary between small side leak and normal data fluctuations. This is the end of my speech. Thank you for your attention.